So welcome to the PhD dissertation talk in defense for Prasad. Excuse me, chips in my throat. And so I just wanted to mention before he starts, it's been a great pleasure to work with Prasad for the last 5.5 years, almost 6 years, I guess, coming up now. Is that right?
This is close to 4.5.
4.5?
Yeah.
Okay, time flies.
It's all feeling now.
You get old, I guess you forget when it actually all begins and everything. Anyways, Prasad, after he leaves here, hopefully successfully defends today, he'll be taking up a faculty position in an institute in Sri Lanka. So Arthur C. Clarke will be proud of him. And so today he's going to talk about exploring star formation and cluster galaxies. Please give him a warm welcome.
Okay, thank you. So my dissertation topic is exploring star formation in cluster galaxies. So I have organized it into few sections. So first of all, I will talk a little bit about the cluster environment and about the star formation inside cluster environment, and then the observations that we did for this project and the steps that I did for all the data reductions, and then the results we have and the conclusions. And here is a galaxy cluster which we called as Abell 426, and this galaxy cluster is around like 78 megaparsecs away from us, and if I convert it to miles, it will be 2 times 10 to the power 19 miles away from us, and this is at the redshift of 0.018, and the galaxy right here at the center, the brighter one, we call that as the brightest cluster galaxy, or BCG. And some of the properties of the inside galaxy clusters is galaxy clusters are one of the most massive, mainly virialized structures in the universe. And they have hundreds to thousands of galaxies bounded by gravity. And typical mass of a galaxy cluster is more than 3 times 10 to the power 14 solar mass. And they have been identified as strong X-ray emitters, and the gas located in between galaxies. So there are not only galaxies inside the cluster, there is gas in between the galaxies, and this gas is known as the intracluster medium. And it is also interesting to note that the most of the normal matter or the baryons are inside in this intracluster medium, not inside galaxies. And so I'm going to talk a little bit about dwarf galaxies, because this is one of the main focus on my research project. The dwarf galaxies are small in terms of intrinsic size, and they have a low luminosity, and they have a very faint surface brightness. And the Large Magellanic Cloud, which we all know is one of the most massive dwarf galaxies that is close by, which is around 63,000 light years away. And so dwarf galaxies are divided into several different types, such as dwarf ellipticals, dwarf irregulars, and dwarf spheroids. And also these dwarf galaxies are the most abundant type of galaxies in the universe, and they are mostly found in groups and clusters. And the problem is, since their luminosity is very low, they are very hard to detect from telescopes. So we need like larger telescope to detect these type of galaxies. And here is one of the important relations about if I compare the field galaxies with the galaxies inside the galaxy cluster, the mixture of galaxies are different inside galaxy cluster. And for this graph, the y-axis is the fraction of different type of galaxies, and the x-axis is the normalized virial radius. So what I have shown here is this, the red color line is the early type galaxies, which are like elliptical galaxies. So the number of elliptical galaxies decreasing towards the outer region of the cluster, while the late type galaxies are increasing. So late type galaxies are mostly spirals. So they are increasing to outer region of the cluster. So we see this particular relation only inside the cluster, so not in the field. So which tells us something that the cluster environment is different than the normal field galaxies. And there are some important mechanisms that I can talk about inside the galaxy clusters. So one of that is galaxy harassment. And the galaxy harassment is if there is a collision, collision can change the gravitational potential of one galaxy due to the flyby of another galaxy. So when this happens, the matter can get heated up inside the galaxy and they can expand. And so this makes these galaxies less bound gravitationally and more prone to the tidal forces. And here is an example video of that. And this is a famous galaxy which we called as cartwheel galaxy. So what happens here is the galaxy right at the center, and there is another galaxy going through that. So when that happens, the structure of this galaxy changes due to that. So the matter get expanded. So I can show that again, the whole video. So this is an example of galaxy harassment. And here is another example, which is the same galaxy, the same cartwheel galaxy taken from the Galaxy satellite, which is basically the ultraviolet. And this image, actually, they have combined several other satellite images together. But mostly I need to point out that the blue light here is coming from the ultraviolet light. So which means if you have, here this is like high star forming regions. So which means if we have, so the ultraviolet light is showing us that there are some high star forming regions here. And another mechanism that I can talk is ramp pressure stripping, which is one of the important ones inside clusters. The ramp pressure stripping is interstellar matter of the galaxy that moves through the intracluster medium will feel the ramp pressure of the intracluster medium. Interstellar matter will feel the intracluster medium. So the interstellar matter is inside the galaxy, and the intracluster medium is the medium between galaxies inside the cluster. And ramp pressure can give from this equation roughly. PR is the ramp pressure term, and the rho ICM is the density of the intracluster medium, and V is the relative velocity of the galaxy. And if this is the self-gravity of the galaxy, so if the self-gravity of the galaxy is, can be given from this term, if G is 2 phi equal G sigma S, and these two terms right here, sigma G and sigma S, are the surface densities of gas and stars. So what happens here is, if the ramp pressure is greater than the self-gravity of the galaxy, the galaxy will be stripped of its interstellar matter. So if there is no interstellar matter, it will truncate the star formation. So that's one thing can happen. And even though I haven't mentioned here, the reverse can happen too. If the ramp pressure is smaller, so it can actually increase the star formation if the other thing happens.
Can I ask you what you mean by surface?
The surface density?
Well, surface of the galaxy.
This is the surface density, like the outside surface.
How do you determine the surface? Where the surface is?
Just if you think about like sphere, here is the surface, like that.
Okay.
Yeah. And this term right here, I can show you an example too, for the ramp pressure stripping, which is this one right here. This is a simulation run in the rest frame of the galaxy. So which means the galaxy is moving towards the center of the cluster. So when the ramp pressure increases towards the cluster, all the gas is stripped away from the galaxy. So that's what happens. And here is an example like an observation from the RAM pressure stripping. This is a galaxy cluster Abell 3627, and there is a galaxy inside that falling towards the center of the cluster. So when it falls towards, this is the zoomed section of that galaxy. So we can clearly see that some of the gas has stripped away from the galaxy. So what has happened was initially it has start forming stars, and then all the gas has stripped away due to the RAM pressure stripping. So the purple color that you are seeing here is all the H alpha emitting gas. And so the main objective in my project is to study, quantify the impact of the high density cluster environment on galaxies by measuring their star formation rates. So the next question is, how can we measure the star formation rate inside these galaxies? So here is the method that I used using the H alpha. The reason is, if we have high mass and high temperature stars forming inside the galaxy, they can emit a lot of ultraviolet photons, and especially O and B type stars. So when they are emitting ultraviolet photon, they can ionize the surrounding hydrogen gas in the interstellar medium. And when they ionize, they will go to higher energy levels, and when it recombine again, there will be the energy emitted which will correspond to the 65-63 angstrom, which is the H alpha line. And if we can measure this one, we can get an idea about the star formation rate, because the H alpha is related to the ultraviolet photons emitted due to the star formation of O and B type stars. So that's the idea. And so how do we measure the H alpha emission? So we use the large 4-meter telescope in the Kitt Peak National Observatory to measure, take images to measure the H alpha emission of these galaxies. And here is an outside view and the inside view of the telescope. And basically we have used two filters. One is called R band, which I will explain in next slides, and the other one is a narrow band H alpha filter. So the reason that we select the Kitt Peak observatories, they have this, the largest telescope they have is this large 4-meter telescope, which is a reflecting telescope, and it is close to the summit, just below the summit of the Kitt Peak, so which is a very good place for observing. And Kitt Peak is also known as for its good seeing value, and the seeing value means in astronomy is the blurriness of star-like objects, because we have to have a good seeing value to get good images. So basically, if you are observing a star, it should be a sharp one. So if the atmosphere changes, the stars get blurred. So that's the idea. And also the Tucson city itself have some bylaws regarding the light pollution, so which reduce most of the light pollution around that area. So this is very good, because we are basically focusing at low mass, faint galaxies and faint objects. So this is a good place for observing. And here is the cameras that we used, basically CCD cameras. One is called Mosaic 1.1 imaging. Both of these are CCD cameras. This is Mosaic 1.1, and this is called Mosaic 3 CCD camera. Sorry. And so each camera can have, this camera has 8 CCD chips, and each CCD chip has 2 amplifiers, so which makes it altogether 16 amplifiers. And this CCD camera has 4 CCD chips and 4 amplifiers for each CCD chip, which makes it again 16 amplifiers. And here are the 3 filters that we use. So we have a 1 broadband filter, and then we have 2 narrow band filters. And the reason that we have 2 narrow band filters is depending on the galaxy cluster that we are observing, they are redshifted. So which means the line, the H alpha line itself is redshifted. So we need to take that into account when we select a filter. So which means when we have a high redshift galaxy cluster, we have to use this shifted filter for those galaxy clusters. And the reason that we are taking images from two different bands, even though we have to have H alpha flux, I will explain that later because there is a reason behind that. And here are the galaxy clusters that we have observed. And so each galaxy cluster we use two filters depending on the redshift, and you can see here that the two clusters that I have higher redshift values, I use a different filter, which is that shifted one because of the redshift of the galaxy clusters. And here are the locations that we observed on the sky in terms of the right ascension and declination values. And the next is the data reduction part. So normally these astronomical images are read as FITS files, which is an abbreviation for Flexible Image Transportation System. And for these particular cameras, since they have several chips and amplifiers, they are actually read as multi-extension FITS file, which means there will be a FITS file for each amplifier. So which makes it little harder to reduce the data using normal softwares. So there is an option in the image reduction analysis facility, or we call this as IREF, to reduce the data. And there is a special package inside that called MSCRED. So we use that to reduce all this data. And there are some calibration steps before we do any basic data reduction. The first one is the crosstalk effect. So the crosstalk effect means since there are 16 amplifiers, and when the data is read to the analog to digital converter and into the computer, they all read the data at the same time. So which means when the data is reading through, the effect signal in one amplifier is affecting to the signal in the other amplifier. So which create these ghost type images on the ghost type signs on the image. So we need to remove those signs from the image, and this is called the crosstalk effect. And to remove that, we found crosstalk coefficients and apply those to the images. And here is a brief equation that we use to find the crosstalk coefficients. So basically the idea is you take IV is called the victim amplifier, or the intensity from the pixel from the victim amplifier, and B is the background level of that particular read line, and the IS is the source intensity from the source amplifier. So using this we can calculate the crosstalk coefficients and apply those crosstalk coefficients to the image. And once I apply it, this is the result. So most of the higher, brighter crosstalk coefficients are gone in this image. And so once I am done with that, I can go to the apply for the bias and flat field images. So the idea is the bias is any camera has its noise level on the chip. So we need to remove that. So to remove the noise level, we are using bias frames. The bias frames means you close the shutter of the camera like it's like 0-second exposures, which means you shouldn't have anything. You should just have the noise level of the camera. So that's the idea. And the other one is the flat field images. The flat field images means for any camera, if you take 2 pixels, they have a slightly different sensitivities. Even though you make a perfect camera, you have a slight different sensitivities from 1 pixel to the other. So we need to normalize that. So what we are doing here is we are taking, we illuminate a screen from a uniform light and take flat field images separately. And this is also a filter dependent or the wavelength dependent, which means we need to do it for both filters separately. And then we take several, 7 or 8 flat field images like each day, and then average it out to take the final flat field image. And once I have all these flat fields and bias frames, I can apply that to the raw image. So I'm going to reduce the noise level and normalize for the pixel to pixel sensitivity variations. So this is done through this equation when I apply the bias and flat fields. And this is called the corrected flat field. That is because there is a special thing about this mosaic camera in the Kitt Peak Observatory. They have this bright ring structure in the flat field image, which I have to remove because it is not came because of the flat field image itself. they have an issue that they have mentioned that they have a ring structure on the flat field images. So I modeled it and then removed it separately. And here is the output after I applied all the flat and bias fields. So here is the raw image, which means you open the telescope and take the image, and this is what you get right away from the telescope, which is called raw image. And once you apply the bias and flat fields, you can remove all these gain variations that you see in, from one amplifier to amplifier, these kind of things. So here is the output. And the next step is to convert the image coordinates that I have in the pixels to WCS coordinates. WCS means the world coordinate system. The idea is when I have an image that I open it in the computer screen, it basically tells me the X and Y, which is the image coordinate, local X and Y coordinates, but I need to make sure that which position that I am looking at on the sky. For that, I can convert all these image coordinates to the world coordinate system. This is called like refining world coordinate system, because telescope itself has some information about the world coordinate system inside the image header. So what I am doing just here is, if I saw that it is not accurate, I am going to make a small correction for that. So that's the idea is you convert the pixel coordinates to WCS coordinates. So that's what we do. And the final step for the data, like the basic data reduction, is stacking images. So basically, we took 300-second exposures like 5 times. And these 5 times, when we take each image, we have dithered the camera. So which means you shift the camera a little bit and shift again like that for 5 positions. The reason is, as you see here, there are gaps between inside the CCD, between CCD chips. So you need to cover that. And also, when you have 5 images, once you stack it, it will increase the signal to noise ratio of the signal level of the image, and also remove the cosmic rays and bad pixels. And we also use the IRAF for this particular task, which is called the MSC stack. And also the reason that I have accurate world coordinate system here, so when you stack the images together, that is the standard coordinate system, because each image will have the same coordinate in terms of the right precession and declination. And okay, so the reason that we have 2 images, one from the broadband and the one from the narrow band, is mentioned here. This is called continuum image subtraction. And the idea is, now I have a broadband image and then I have a narrow band image, but narrow band image has some kind of width of the filter, which means you can get the H alpha line, but it will have some other flux coming from the R band as well. So I need to remove that, because if I take the direct image, it will be a flux from the R band plus the H alpha line. So the idea is I need to remove that part to get only the H alpha line. So to do that, here is what I'm going to do. That is, you take the narrow band image, this is H alpha n, and then you take the R band image from the same cluster, and then you multiply it from a scaling factor, which I called as C. So when I do that, the subtraction, I can get the pure H alpha flux, and here is how it works. You get let's say your flux level from the R band is right here, and if the narrow band filter is this narrow rectangle right here from the blue color and the green dashed color. So the idea is, if I have an object that has some kind of H alpha flux, it will be recorded here in this rectangle, which means you will have some kind of H alpha flux above the R level, the red flux level, but it will also record this amount of flux for the R band as well. So I have to remove that. The idea is you can scale this image, that is you take from the R band, so that flux will be equivalent to this small rectangle that I shown here from the green red color, enclosed from the red line and the black line. So that's the idea. now the problem here is how do you scale this? What is this scaling factor? So we need to figure out that one. And so as I show you here, so we are basically scaling and subtract the two images. So first I need to think about the scaling factor. I have to think about how to subtract two images and how to scale one image before I subtract. So I'm going to talk about image subtraction, then I will come back to the scaling about the image. And when I go for the subtracting images, there is another problem here, because when I took each of these, like when we start observing these images, like 300 second times 5, it will take some time. And after that, I have 600 second exposures for the narrow band. So which means the time pass, the atmosphere condition changes. So the seeing value changes. So which means if I look at one particular star from two images at the same location, they will have two seeing values, which is basically the full width half max value of these curves. So this is called the point spread function. So which basically, this axis shows you the pixel count or the flux value, if you think about it in that way. And this is what will happen. So at the center of a star, you will have a high flux value because the brightness is high and it will decrease. And if you look at the full width half max values of these two stars, so one has 1.26, the other one has 1.36. Now, if you subtract these two straight away, what will happen is one star is spread out and other one is like very concentrated. So when you subtract, you will see a small ring structure, so which is not good for the rest of the project. The other thing is, since the mosaic images are also larger, so their point spread function is changing, or the seeing value is changing from one corner to other corner as well. So I have to take that into account as well. So we use a software called higher order transformation of PSF and template subtraction, which is also called as abbreviated as hot pants. And the idea is this particular program was capable of take the image that had the bad seeing value, so they take the image that has the good seeing value, and it can convolve that image so that it will equal to the bad seeing value of the other image. So basically, that's the whole purpose of having this software. The reason that we choose specifically this program is it is capable of dividing the image into like several sections and looking at each section separately and convolve that section by comparing the relevant section of the other image, because the PSF function is varying throughout from one corner to the other corner. So one PSF or like the one kernel for the whole image does not work in that case. So this program can divide the image and then convolve the image like each section separately, so that we will have separate kernels for each section. And the one that I show you before, the scaling factor right here, so that comes into business next. So to find the scaling factor, we use a method. So we assume that the foreground stars that we have are non-H alpha emitters. So when we assume that, so what happens is, if you take one star, like a foreground star from the narrow band image and the broad band image, they both should have the same flux. So what we are doing is, based on that, so on average we think that it both have the same flux. So in order to make into account that, we measure the flux from the narrow band image and the broad band image, and we scale the R band image so that they will have the same flux. So what I have shown here is the flux ratio of the two filters of those stars after I scale the R band image. So which is close to 1 on average. So this is so we use like 160 stars for this one. So just to make sure it is statistically correct. And once I have all these things done, here is the result. Here is the first section of this image is taken from the narrow band filter, and this one right here from the broad band filter. And once you match the seeing and scale one image and subtract those two, here is the result. And you can see this large galaxy right at the center, it has some kind of H alpha flux which is recorded here. And if it doesn't have a alpha flux, if you can see, I don't know, it's not clear. For example, this particular object right here, you can see it here, but you can't see it here. The idea is that doesn't have any H alpha flux, so it is completely subtracted. So only the flux remaining in the H alpha will be seen here. So that's the idea. So once I have this fluxes subtracted image, I can go and measure the magnitudes. So we use a picture processing package to measure the magnitudes. The picture processing package is an interactive program that it can read the FITS files, and also it can detect all the objects in the cluster image. And also once it detected object, it can measure all the instrumental magnitudes. And the important thing here is it can also classify the stars and galaxies. So these are like hugely crowded fields, so we need to find the statistical way of classifying stars and galaxies, because we are looking at galaxies only. And here is an example of detecting objects. Once I run through the image through that program, so if I select, when I set the background level, it can select all the objects inside that particular cluster image. But sometimes it also select these bleed trails as objects, because it is just a program. So it takes the maximum values and measure the maxima like local locations, and then detect all the objects. So what I did here is there are like 30,000 objects in each image, and I go one by one each time. And so if it marks all these bleed trails as objects, so I cleaned it manually myself. And then so I did this for like all 10 clusters and all the filters. So which I can make sure that I have a clean object file for the rest of the work. And here is then it can measure the magnitudes, and then here is how it can identify or separate stars and galaxies. The program calculates a parameter called C2, which is given from this equation, and this Mi asterisk, that is the magnitude measured from a reference star that we select, and this Mi is the object that we need to classify. The idea is, if it is, let's say you have a reference star, and if you have another star, these two values will be roughly equal. The idea is it will make the growth curves and then try to look at the difference of the growth curve. That's how it works simply. So if the difference is close to 0, so here is the line that they have stars. This axis is the value of that C2 value, and this axis for the instrumental magnitude. So if we have values close to 0, which forms this line, so they are all stars. And right here, this region, so they are called as galaxies. So basically, depending on the value of the C2, they decide which one, the program decide which object is a galaxy and which object is a star. But when it goes to the faint end, like this region, you can see this star sequence and the galaxy sequence both merge together. So when this happened, the other thing is, when you go for the faint end, so there are a lot of stars here which we do not normally expect. For the faint end, the number of stars should be lower than the galaxies. So in that case, what we are doing is, after a certain limit, when it starts to merge, the program divide this into several magnitude bins and try to find the model value of the C2 parameter and make a ridge line like this for that. And then it takes 1.2 sigma value and make another line in this line like that. And all the objects in between these two lines are also taken as galaxies for the faint end. And here is another thing I did. When I look at these images, you can see there is a brightest cluster image right at the middle of the cluster. So each cluster has this BCG. So what happens here is, some of the objects in the cluster image is surrounded by like objects around this the BCG we cannot see it because of the halo of the BCG. So these objects are covered. So if I run this section through the program, it won't be able to like measure these magnitudes correctly of these objects. So what I am doing here is, I model this BCG and subtract it from the image, the original cluster image, and I use this subtracted image to measure the magnitudes of these objects close to the BCG. And so I have all the objects and magnitudes now. The thing is, the magnitudes that we are getting from our instrument, we call those as instrumental magnitudes. So, but we can't compare those to any of the magnitudes in the other surveys. So I have to convert those magnitudes into the standard magnitude system. So what I did was I compared my galaxy cluster sample objects with the Sloan digital relevant objects in the Sloan digital sky survey, which is already calibrated, and I adjusted the photometric 0 point. So the idea is once you adjusted that, you kind of add some kind of value for that, so that to instrumental magnitude, so that the difference of my magnitudes, which I given here as MKPNO, and MSDSS means the magnitudes from the Sloan digital sky survey. So the differences will be approximately equal to 0 when I calibrate those objects for the Sloan digital sky survey. And the next thing is look at the completeness limit. Now this y-axis right here is the number of galaxies in the log scale, and the x-axis is the magnitude, the calibrated apparent magnitude, which will the brighter objects will be here. It will be fainter when you go to the x direction. The idea is astronomical magnitudes are measured in the reverse order, so the brighter ones will be fainter. So the idea is you can see the number of galaxies will increase towards right here, and then it start decreasing. The reason here is it's not that the actually galaxies are the number of galaxies are decreasing. This is since we have a specific integration time, and the telescope is have a certain limits, like it's like 4 meters, so it can't measure some of all the faint objects that you can see. So after certain limit, it will drop down because of that. And so I need to make sure my sample is complete. So I cut off all my data 0.8 magnitude brighter than this maximum value to make sure that my sample is 100% complete when I look at the results. And the next thing is, now I have the galaxies, all the galaxies selected from the cluster images. But how do I know which galaxies belongs to the cluster and which galaxy is not? Because I am basically looking at 3D, the two-dimensional image of the 3D world, right? So some of the galaxies right here will be projected to this plane right here, which I am looking at. But they will be at different distances. Some of may belongs to the cluster and some of may not. So I have used this galaxy red sequence method to make sure that I have a statistically correct sample as correct sample for cluster galaxies. So what happens here is if we measure the magnitudes in 2 different bands for the same, this is called like a color magnitude diagram. The galaxies that belongs to the cluster will form a tight sequence like this. So this is called the red sequence of galaxy clusters. And this has seen for each cluster. So that is a characteristic of a cluster. So people have used this method actually to find the galaxy clusters, like when they do surveys. So what I did was I didn't have one of these bands, which is called G band, and I matched all my objects to the Sloan Digital Sky Survey and took the objects from them, and then made this color magnitude diagram, and I saw this tight red sequence, and which means these galaxies belongs to the cluster. So what I did here is, the next thing is I rectified this particular line so that it will translate and rotate a certain amount so that the slope will be 0 and it will be right here at the 0. Then I make a histogram. So I think this graph is not clear. So this axis right here, it's mg minus mr or g minus r, which is basically the y-axis right here. And the x-axis is the number of galaxies in each magnitude, like each different bin in this y-axis. So the idea is when I make that, I can fit the Gaussian curve to that histogram. This is a histogram. And once I fit the Gaussian curve, then I can measure the standard deviation of the Gaussian curve. So once I have that, I took the plus or minus 3 sigma of this red sequence line as the galaxies that belongs to the cluster. So this is like a statistical measure just to make sure that I take the galaxies belongs to the cluster, but not take like not go like a lot further away, so that I will include like contamination for the sample. And I also the best way to like figure out which galaxies belongs to the cluster and which galaxies not belongs to the cluster is use the spectroscopic data, which gives you like accurate redshift values. But the problem is we don't have any spectroscopic data for faint-end galaxies, but we have some of the data for bright galaxies. So I took the spectroscopic data from the Sloan Digital Sky Survey when they are available for brighter galaxies. And the red circles I have shown here is all these data taken from the spectroscope from Sloan Digital Sky Survey. So I just checked whether they are matched with my selection with the red sequence galaxies, just to make sure that the results are accurate. And also I use, for the calculations, I have used the standard concordance model, which gives me the Hubble constant is 70 kilometers per second per megaparsecs, and the omega lambda is 0.7 and the omega m is 0.3, and all the magnitudes that I have talked up to now is in terms of apparent magnitudes. So before I compare anything else, I have converted everything to the absolute magnitude, which is capital M here, using the luminosity distances, and the mu and k here are the corrections for the extinction and the k correction. The k correction means we are measuring like galaxies at different redshifts, so we need to take that into account when we have the absolute magnitude. So that is the k correction, and the mu is the extinction correction. And then also I have defined a value called R200. Now the idea here is the galaxies are at different redshifts. So if you image a close by galaxy, you will only see a central region, and if you go further, you will see a galaxy like you can go further out. So that's the idea. So if I am going to compare the edge of one galaxy cluster to the edge of the other one, it will not work. It's like when I image it, this if you think this the large figure as the galaxy cluster that is close by, you may image it up to here, but the one that is further away you can image up to the head. So if you are comparing these two limits, you are like comparing different regions. So in order to make sure that I compare the same regions on the cluster, I have normalized the radius, cluster-centric radius, which I am going to measure from the center to the outskirts from this R200 value. And this is roughly the 200, the radius where the galaxy cluster has the 200 times of the critical density. And here are the some basic conversions I need for my calculations. Basically, the apparent magnitudes can be converted to the H alpha flux using this equation. All our magnitudes are in AB magnitude system, because we calibrate our values against the Sloan Digital Sky Survey, which is from AB magnitude system. So our values should be from AB magnitude system. And I have made 3 basic measurements for the star formation rate. One is the equivalent width, which is defined as the line flux divided by the continuum flux density. And the star formation rate is calculated using this equation. So once you have the luminosity of a certain galaxy, it can be converted to a star formation rate using this conversion factor. So this is called the Kennick-Tiggott relations. He has derived this relation like, I guess, 30 years ago, and this factor, if I multiply this factor from the luminosity, it can give me the star formation rate values. Here is how I calculate the star formation rate, and I also looked at the specific star formation rate, which is defined as the star formation rate per unit stellar mass. And for the results, this is just the red all the galaxies that I have in my samples once I converted it to the absolute magnitude values. And the one thing that I am looking at here is when I am selecting the red sequence galaxies only, so my sample is a little bit biased, because it will because the red sequence will not contain some of the spiral galaxies that will belong to the cluster, because the spirals are normally have larger star formation rates, which means they will go down that red sequence plot a lot below, because they are a lot bluer. And what I am doing it here is there are some of the galaxies inside the red sequence, like especially the spiral galaxies. So I needed to check whether these spirals are red. Is it because of dust, or is it just because they are passively star forming, like the low star forming? And what I did here is, here is actually the paper that actually Lane is working on this one. So he has measured, here look at some of the red sequence spiral galaxies and look at the color magnitudes from the WISE or wide infrared satellite image. So WISE data. So all these red dots right here are the spiral galaxies that are in the red sequence. And the color values go from 0 to 3.0 up to here, and it will around like 0.2 here. Here is the same graph that I took from the directly from the WISE paper. So they have mentioned that if we have some kind of dust in the objects, the dusty object should be go around this region, and if it not, it will be around this region. Now these all galaxies, since they are like around like 0 to 3.0 and between 0 to 0.1, this is the same, both axes are the same in both graphs. So those objects should be lie around this region right here. So which clearly tells that they are red. It's because they are actually passively star forming, not because of the dust. So that's one thing that I looked at before I consider about my results. And here are the results I got. And I measured, once I have all this H alpha flux, I measured the star formation rate with the cluster centric radius. That means the normalized radius from the R200. And so I have seen that the star formation rate is decreasing towards the center. Here is the center of the cluster, and it goes to the outerward. And also I looked at the equivalent width. It shows me the same trend, that it is decreasing towards the cluster. And here is the specific star formation rate measured with the cluster centric radius, and it has the same trend, that it goes down and decreasing towards the cluster. And my main concern is look at the dwarf galaxies. This is all these three plots for all the galaxies inside the sample, which includes both giants and dwarfs. So I divided my sample into giants and dwarfs. So which means I decided to use minus 17, all the magnitudes fainter than minus 17 as the dwarf galaxies, and the brighter than that will be giant galaxies. And I also looked at the dwarf galaxy density, change in the dwarf galaxy density with the cluster center. So when you go outward, the density is decreasing. So which is consistent with some of the published results. So I just need to make sure that since we are using the statistical method, like for the classification, everything is correct at this situation. So here is the interesting result that we got. When I looked at the giant galaxies and dwarf galaxies separately, the giant galaxies did not show up any trend towards the center. But for the dwarfs, there is a clear decrease towards the center, which clearly shows me that the cluster environment have an effect on dwarf galaxies than giants. So that is the main thing that we observed. And I also I fitted a line here. So for these data points, so what I have done here is, for each radial bin, I have used the median value, which is given in this red dot. And for each median value, I have find the median value, and then I fit a line for that median values. So that's what I have done here. And also I also looked at the equivalent widths, but they kind of roughly showed me the same trend, while the giant is a little bit larger than the dwarfs. But since the values are small, I figured out that they become like less sensitive when you go for the very small values. And I looked at specific star formation rate, which is the star formation rate per unit mass, which gave me this result, which is completely reverse what I have seen from the star formation rate. So the specific star formation rate, I have a larger gradient for the giants, which is roughly 3 times than the dwarfs. So this has a larger gradient. Now the reason is, this is for a specific star formation rate, which means that you are measuring the star formation rate per unit mass. So for the unit mass, you have a large gas content inside the giant galaxies than the dwarf. So which makes sense. And also I used probably you have seen that the code that Madina presented like 2 weeks ago for the morphology density, like classification of galaxies. So I used her code to divide my giant galaxies into ellipticals and spirals and look at whether there is a effect in terms of the morphology of the galaxy when it comes to the cluster environment. I roughly see that the same trend for both giant ellipticals and giant spirals. So I concluded that there is no significant difference in terms of the ellipticals and spirals. And also the data is a bit scattered because once you divide into several sections, the number of data points gets smaller. And also the morphology density relation that I talked earlier. So I have looked at the morphology density relation for my sample as well. And I show that the same relation at the center of the cluster, which means there are higher number of ellipticals and smaller number of spirals. And when I went to the outer radius, which you would normally expect this red dot should go up and this should go down as per the morphology density relation, but I did not see that. And then the reason is I am selecting only the red sequence galaxies, which means I am eliminating the high star forming spiral galaxies from the sample already. So which makes sense that I don't have any large number of spiral galaxies in this region to show up. And then I tried to compare my results with some of the published results, and here is the one from the Gomez and his group. And the important thing to note here before I start is all these studies are done for giant galaxies only. There are no studies done for the dwarf galaxies. So it is completely new one. And for the giant galaxies, I saw that they have a decrease in the star formation rate. But in my case, if you remember this plot right here, I didn't even see this decrease is very small. And the reason again is when I looked at their paper, they have selected a volume limited sample, which means they look at spectroscopic data and have taken both spirals, like star forming spirals in the outer region, and also the elliptical galaxies, which I can explain in that sense that they should have a little bit more star formation rate in the outer region. And this is a study published from Blalog et al. Once again, the same thing. They have used the spectroscopic data for giant galaxies. As far as I remember, they have gone like 1 magnitude fainter. The previous one was like 20.5 magnitude, and this one was, as far as I remember, this is close to 19 or something like that. So he has seen the decrement of the star formation rate as well. And 3 other lines right here, different models that he tried, and it also shows the decrement of the star formation rate values. And here is the comparison between one of the published results for the specific star formation rate, and here is from, I think it's Van der Linden. And he has categorized his sample into several mass ranges, and the red one right here is the one for the larger masses, so the giant galaxies. And I can see that here is a large drop towards the center, which I roughly see that drop in my giants as well, while the dwarf did not show up any specific drop in terms of the specific star formation rate. And this y-axis right here is specific star formation rate, but they have mentioned it as star formation rate per unit mass. So that's it. It's the same axis. And also these 2 graphs I have shown you before, but they were not in the log scale, so it is the same graph. And to conclude this, so I have the conclusion is the decline of the star formation rate is consistent with both published studies. This means the studies that I looked at, the 2 studies, for the complete galaxy sample that I have used. And the dwarf galaxies were found to be more affected by the ramp pressure stripping than the giant due to their low mass. So that's something that I clearly show in my sample. And I didn't see any enhancement in sample, like the star formation enhancement. The reason maybe it could be masked by the large uncertainties due to the scattering of the data, because we have only like 10 samples. So it's not adequate to decide whether we have tell that whether we have only decrement or whether there is an enhancement on the way. And the decrease in the star formation rate is essentially identical for both ellipticals and spiral galaxies. And so the environmental effects such as ramp pressure, so these are more influential for giants in terms of the specific star formation rate. So this is different. And the reason is there are more gas inside the giant galaxies than the dwarfs. So for the unit mass, specific star formation rate should be larger. And in terms of the galaxy harassment, because I show you two things, the harassment and the ramp pressure. So star formation rate, effect of the star formation rate is inconclusive due to the larger scatter in the data, because there are published results that you sometimes see enhancement and then decrease of the star formation rate due to the galaxy harassment. So I didn't see that. And one thing to note here is that my whole sample is biased against the galaxies having the large amount of star formation, because I excluded, since I am looking at only the red sequence spiral, red sequence galaxies, I have excluded some of the large star forming galaxies that is in the sample. So, and in the future, so this is one of the studies that specifically looking at the star formation rate of dwarf galaxies using H alpha. And I didn't find anyone looked at this kind of study for the dwarf galaxies. And if I can increase the large sample of galaxies for this method, I probably will be able to get more improved results in terms of the Poisson uncertainties. And also we expect to look at expect to use this 30-meter class telescope, which will be built in future, probably next few years or next decade, to conduct a detailed spectroscopic study for the star formation in the nearby galaxy. The problem right now we have is there is no large telescope to look at the spectroscopic data for these type of dwarf galaxies. So these kind of statistical method are the only available tools up to now. And the other thing is what happened to this gas that is disrupted from the dwarf galaxies. So we try to look at this dwarf disrupted galaxy model, which tells us that there is a halo around the CD galaxy or the BCG galaxy at the center. So these disrupted gas maybe have contributed to the halo of that BCG galaxy. So we can, if we can look at the color gradients of both dwarfs and the BCG galaxy halo, we can check that. And yeah, so finally, I would like to especially thank to my advisor, Dr. Wayne Barkhouse, for his all the help throughout the last few years, and all my committee members and Department of Physics. And also this is funded by NASA EPSCO program. And also I have given funded from National Optical Astronomy Observatory, so I especially thank to them. So they provided all my travel expenses and everything for observing. And I would like to thank them as well. So thank you all for listening.
Questions? No?
Yeah. Yes, I'm interested in something about the two band filters that you used.
Yes.
And I think you used those to discriminate between the alpha emission and other emissions. Is that the idea?
No.
Okay, maybe you could just...
Yeah, I can explain that.
Right there. Yes.
These two, right?
Yeah.
The idea is if you, since the galaxies are if you look at one galaxy cluster and another one at a different redshift, right?
Okay, yes.
And these two are at different redshifts. So sometimes if you look at the H alpha line coming from this galaxy cluster, is it different wavelength than that one. So there are two clusters that cannot handle, if you look at this filter, there are two clusters that H alpha line doesn't fit into this filter. So I have to use another one.
There are two clusters right now.
Can you see this redshift right here?
I
So there are two clusters that have higher number of redshifts,
yes.
right?
Those, yeah.
So these two have, the H alpha line is shifted more than the other 8 clusters because of the larger redshift, right?
Okay, so they have larger than the others.
Yes. So for those two clusters, I have to use a separate filter because that H alpha line is not here, it is shifted to this filter. So for example, if I use this filter, you won't detect anything in terms of the H alpha because those two clusters are like redshifted completely.
Yeah, okay.
Yeah.
Yeah, I thought there was something else going on. All right, fine,
Yeah,
I see
yeah.
that, that's good.
Yeah.
Any other questions?
Just a general one. So are your filters electronic or are they physical?
They are just physical filters. The electronic filters what you find in these digital cameras.
Any other questions? Don't be shy. One last time, any other questions? If not, please thank our speaker. Okay, at this point, I'll ask the committee to